Hello again, students. Picking up from where we left off, we are trying to look at how to make polar graphs, to graph in polar coordinates when we have a polar equation. So in the beginning, it is good to practice going point by point, just plugging in values for theta, seeing what you get for r, plotting points, and seeing what you get. As we did, for example, in our last example of r equals theta, where we got that big spiral. But that can be a bit cumbersome and time-consuming. So a more general method for still doing this yourself by hand to get an idea of what's going on, other than just turning to technology to do it for you, is to, let's put up an example here, is to take a polar equation. Let's say we had r is equal to, I think there's a good example in the book I wanted to use. So let's look at example 6, which is on page 726, where we have r equals 3 sine of 2 theta. So it's quite common when you have polar equations that instead of theta just occurring by itself like an x or a y variable, that since it is an angle, that it shows up in the equation in some sort of a trig function, like sine or cosine, and that'll be very, very common. And let's also remind ourselves that in general, x is equal to r cosine theta, and a little messy here. There we go. And y is equal to r sine theta. So having a cosine or a sine gives a little bit more natural relationship between the normal Cartesian system and the polar system. But so looking at this example, r equals 3 sine 2 theta, if we wanted to graph this, I could set up a table of values and I could start just plugging things in and seeing what I get. And even some of that is still good to do. But as I was demonstrating a little bit, to transition between the angle values and to connect the dots, sometimes it's helpful to see sort of the pattern that you're going to get, especially if you have a trig function, because our trig functions are fairly well understood. So, for example, if I have theta, and I'm going back and then getting r based on my theta value, I know this is right to left, I can still start with a 0 and see that sine of 0 is 0, so I would get 0, so I know I'm starting at the origin here. But then what I do is I imagine what the values of the 3 sine 2 theta would give me before I try to translate to the graph. And so the book will show you this better than I can by drawing it by hand. But what you could do as you're imagining these points being generated is you could imagine sort of what this would look like as you plug in values of theta, what you would get for r. You could map those where theta is not an angle, but where theta is just like an x-axis or a vertical axis, and make a sort of a normal graph of the function 3 sine 2 theta, as if you were doing it in a Cartesian system, and then translate the ups and downs of your graph into r values on a polar graphing system. So, for example, we know 3 sine of 2 theta basically goes from 0 to pi. Since there's a 2 in the argument, 0 to pi is the full period of the function. And with a 3 multiplied out front, we know it maxes out at 3 and goes down to negative 3. You have pi over 2 in the middle, and that you get this sine function. Something like that. So we can then imagine is that I cycle through these angles what my r value is going to be, and then we can graph those. So for example, as I go from 0 to pi over 2 in my angle, we can look and see that what the r value is going to do is it's going to go initially up to a value of 3 at the peak here. It's going to go up to 3, and then it's going to go back down to 0. And so what that means in terms of my graph is that as my angle goes from 0 to pi over 2, so as theta is going from 0 to pi over 2 in this range here, then my r value should go from where it started at 0 out to 3, which it will hit at pi over 4. So at 1, 2, 3, pi over 4, I'm at 3. I'm going to go out to pi over 3, and then I'm going to go back down to 0 as my angle is going counterclockwise from 0 to pi over 2. Pi over 2, I'm going to get a 3. So then similarly, as I go from pi over 2 to pi, whoops, that was not right. I went back from 0 back down to 0. Losing all my points here. So then as I go from pi over 2 to pi, it's going to go back down to 0 again. But what I can see from my little graph is that when I'm in that range, then the r value is going to go down to -3 and then back to 0 again. So what that means in my polar graph is that as I'm going from an angle of pi over 2 around over to pi, that I'm going from 0 to -3 for r. Now remember, if r is negative, you don't go in the direction you're pointing, you back up in the opposite direction. So I'm starting at 0, and normally if I got up to 3 pi over 2, I would be somewhere around here for my my angle. 1, 2, 3, yeah, that's 3. But because r is negative, I'm going to instead be backing up and be at this point down here in the fourth quadrant. Oops, that's too far, that's 4. There's 3. I'm going to be at that point. And so in order to do that, by backing up, as I first start out facing pi over 2, the curve will start to back up over here until it gets back out to that point, and then it will come back around and end up back there. So this was all produced with negative values for r. That looks a little too nasty to leave it. So it's going to back itself up this way and then come back down in like that. A little bit better. And then what's going to happen after that is that since that's a full period of the function, it's going to repeat its values and do this same thing again. So as I continue to the right of pi, I'm going to get the same loop going up and then down again. So that means that in my polar graph, as I'm going from pi out to 3 pi over 2, which I just passed, I think, as I go from pi to 3 pi over 2, then I'm going to do the exact same thing I did in the first quadrant, where I have a positive r value again that goes out to 3 and back. So that means on the graph, when I'm in the middle, I would be at 3, and then I'm going to go out to 3, and then I'm going to go back. And then when I'm going from 3 pi over 2 all the way to 2 pi, so now I've made a full circle around my polar graph, well, then it's going to do what it did in the second half before with the negative values. So instead of being in the fourth quadrant, the negative r values are going to put my graph back into the second quadrant. And I'm going to do the same thing over there, where I peak out in the middle at 3, and I make sort of this loop to get there. And of course, these should all basically look the same as each other. That's why the graph in the book will look much nicer than mine. But nonetheless, and then after that, I start over again, because when I'm past 2 pi, then I'm still doing another full cycle, and I'll just repeat. And this graph just keeps getting redrawn and redrawn as you go over these angles again and again and again with higher values of theta. So I end up with a graph kind of like this. It's like a 4-leaf clover, and you will see other types of patterns like this when you're working with polar that are quite possible. But nonetheless, this is a sort of a way you can imagine trying to sketch a graph of a polar equation. And one of the ways to do that, as I've written down here, is to really graph the r function sort of on the side as if it was in a typical Cartesian, just to see how the r values fluctuate up and down. and then translate that into your graph in your picture. Okay, so that's example 6 on page 726, and again, they make prettier graphs than I did here. So there's one other thing I'd like to talk about in this video to finish up what we want to look at in 10.2, and then hopefully you guys can hit the ground running and get into these problems and experiment and learn for yourself. So one of the ways to consider how a graph might turn out that's helpful in some cases, not in all, is to look at the equations that I have written here to translate between x and y. And let's remember there was a couple of others between x and y and polar. We also had the fact that a squared plus b squared equals c squared, which translated into x squared plus y squared equals r squared. And we had the fact that you could theta could be found by taking the inverse tangent of y over x. These are sort of two sets of ways to translate from one type of coordinate to another. So using these equations that relate the Cartesian coordinates to the polar coordinates, instead of just converting one point into another point from one system to the other, we could also try to convert polar equations back into Cartesian equations, meaning instead of an equation in r and theta, we could try to go back into an equation with x and y to see if that helps us understand what the graph would look like a little bit. So let's see. Let's try for an example. They have some problems. I'm going to do something from the exercise set. So let's start simple. Like let's say this is exercises are on page 729. And look at 29. So for 29, it gives us a real simple equation. It just has r equals 2. This is a fixed value for r. We've looked at these before. But the goal in the instructions are convert the following equations to Cartesian coordinates. Describe the resulting curve. So if we have r equals 2, maybe we could just do this by understanding what it means to fix the radial length at 2, that we would just get a circle. But you can also look this as a simple starting example of how to convert. So from above, I can solve for r, and I get r is equal to the square root of x squared plus y squared, which I think is the way I wrote it in the earlier video. So if I just swap r out with what it's equal to in x and y, this gives me that the square root of x squared plus y squared is equal to 2. And if I square both sides, then I get x squared plus y squared equals 4, which is the equation for circle at the origin with radius equal to 2. So this is a simple example because the equation is very simple, and hopefully we're somewhat familiar with the format for an equation of a circle. So let's try maybe a little bit more elaborate example. That was 29, just to see if there's something we could figure out here. So looking at that exercise set, let's say we had 31. So in 31, we have r equals 2 sine theta plus 2 cosine theta. So again, the instructions being to convert this into an equation in Cartesian coordinates and identify the graph involved. So in this case, we don't have just an r to convert. We have a 2 sine theta and 2 cosine theta. And so if you have sine or cosine, then you're probably going to want to maybe use these up here to convert in terms of x and y. So real quick, if you see, I can solve these for sine or cosine. So one of the ways to see these is that cosine theta, if I divide both sides by r, would be the same as x over r, and sine theta, similarly, would be the same as y over r. So if I make those substitutions into this equation, then I get r equals 2 times y over r, and 2 times x over r. So this has gotten rid of the theta part, and now I have everything in terms of r and y and x. But I do have these fractions, so before getting rid of the r variable, I would choose to clear the fractions by multiplying everything on both sides by r, because then that, as I distribute, will cancel out these denominators. And then what I'll have is that r squared is equal to 2y plus 2x. And now r squared can be translated into x squared plus y squared. So this gives me that, x squared plus y squared is equal to 2y plus 2x. So now I have a complete transfer over to the Cartesian variables of x and y with the polar variables all gone. And if I'm then trying to look at this and figure out what kind of a graph this is, we hopefully might want to be able to recognize that we can work with this because we have x squared and y squared. And when you have both of those squared in an equation, that usually means you have some sort of a circle or ellipse or something like that. Now we're going to deal with in 10.4 ellipses and circles and parabolas in a new way. But this is stuff that supposedly would have been done somewhere back in advanced algebra or pre-calculus. Maybe you forget, I don't know. But in this example, what we would do is we would set this equation to 0. So I would subtract 2y and 2x from both sides. And so that would give me that x squared minus 2x plus y squared minus 2y is equal to 0. And then the next thing to do, for those who remember it all, even for those who don't, is that you complete the square for both of these. And the way you complete the square is you add in constants here and here. In order to complete the square, and if you add them in on the left, you of course have to also add them to the right to do the same thing to both sides. So then we have to add in the number that would complete the square, and the way we do that is we look at the middle coefficient, the middle term's coefficient, in this case the -2, and you take half that number and square it. So half of -2 is -1, and if I square that I get +1, so that means I would add in a 1 here. And similarly, in this one, -2 is the same number, so I would add in the same number to complete the square, and then I would need to do that to both sides. So I'm basically going to add a couple ones on the left and add a couple ones on the right. And what that does is that allows me to take these new triples that I've created, and they're perfect squares. They can be factored into perfect squares, which is why I chose the ones to do that. So then this becomes x minus 1 quantity squared plus y minus 1 quantity squared is equal, and I add up the two ones on the right side, I get a 2. And so at this point in this format, hopefully we might recognize this as a circle, where it has so this is a circle with the center at the 0 values of the two factors, which is 1, 1, with the radius equal to the square root of the constant. This is basically like x squared plus y squared equals r squared, but the x and the y's have been shifted, and so since r squared is 2, then the radius would be square root of 2. So the graph that I get is described like this, and this is the equation for it. Anyway, so this is an example problem, problem 31 from the end of the section. And so one of the ways you can sometimes see what's going on in a polar equation is to actually convert it into a Cartesian equation. Now, polar equations make for all kinds of graphs that would be very hard to see what's going on in Cartesian equations. So this isn't the standard approach to dealing with polar equations, but it sometimes is used, and you'll have, as we see here, some of the exercises in the exercise set that ask you to do that. But most likely, if they don't ask you to convert into Cartesian, you don't want to. So keep it in mind, this is not the general way to figure out what a graph of a polar equation would look like by converting it, because most of the times, if it's in polar in the first place, it's more easy to work with in polar to see what kind of a graph you'll get. Like imagine that four-leaf clover we looked at a few minutes ago. All right, so that's where the section pretty much ends. So we'll stop at this point, and hopefully I'll do some Q&A with everybody in the coming sessions.